The peak of urbanization had led to the rise in the economic development worldwide, simultaneously stimulate the expansion of infrastructure development. According to the research, about 20 million metric tons of the concrete were consumed per annum, leading it to one of the most man-made material ever used globally. Conventional concrete as a composite substance is the chemically bond of concrete of aggregate water binder as the fundamental constituent material. It is relatively economical and widely available around the globe due to its unique advantage compared to the other material. A significant problem that is currently facing in the industry is the fire resistance that needed in the building structure. Therefore, it is desirable to replace the structural element at the design fire rating lightweight. Fire with the lightweight concrete. Lightweight concrete offers the low dead weight for the construction due to its low density that can be cut down the cost. The main focus in this research paper is to investigate the performance of the lightweight concrete in the term of fire resistance and the strength properties by incorporate different percentage, which is 0, 5, 10 and 50% of the partial lightweight aggregate.
Basic concept of lightweight concrete. Lightweight concrete mixture is made with a lightweight coarse aggregate, and sometimes a portion or entire fine aggregates may be lightweight instead of normal aggregates. Structural lightweight concrete has an in-place density on the order of 300 to 2200 kg per meter cube. Normal weight concrete, a density in the range of 2200 to 2600 kg per meter cube. For structural application, the concrete strength should be greater than 17 MPa. Lightweight aggregate used in structural lightweight concrete are typically expanded shell, clay or slate material that have been fired in a rotary kiln to develop a porous structure. Other products such as air-cooled blast furnace slag are also used. There are other classes of non-structural lightweight concrete with lower density made with other aggregate materials and higher air void in the cement-based matrix, such as in cellular concrete. The basic concept behind the making of lightweight concrete is by inducing the air in concrete. To do this, there are several methods that can be adopted. The first one is by using porous lightweight aggregate of low apparent specific gravity. This type of concrete is known as lightweight aggregate concrete. The second one is by introducing large void within the concrete or mortar mass. This void should be clearly distinguished from the extremely fine void produced by air entrainment. This type of concrete is variously known as aerated cellular foam or gas concrete. Lastly, by omitting the fine aggregate from the mix so that a large number of interstitial void is present. Normal weight coarse aggregate is generally used for this method. This concrete known as no fine concrete. For this study, the previous researcher used oil palm shell as an aggregate in lightweight foam concrete.
For the properties of lightweight concrete, the shape of the lightweight aggregate used in concrete may be in cubical, rounded, angular, or irregular shape. Textures may range from the fine pore, relatively smooth skin to highly irregular surfaces with large exposed pores. Next, compressive strength levels commonly required by the construction industry for design strength is from 3000 to 5000 psi, which can be easily obtained by lightweight concrete. As for the density, the fresh density of lightweight concrete is a function of mixture proportions, air content, water demand, particle density, and moisture content of the lightweight aggregate. For the absorption, studies have revealed that high-quality lightweight concrete absorb very little water and thus maintain their low density. For the internal curing, lightweight aggregate batched at a high degree of saturation may be substituted for normal wet aggregates to provide internal curing in concrete. The thermal conductivity of concrete depends mainly on its density and moisture content. As the lightweight concrete is low in density and moisture conduct is more due to pores, the thermal conductivity of this concrete is less when compared to normal concrete. Lastly, for the fire resistance, when tested according to the procedures of ASTM, structural lightweight concrete slabs, walls, and beams have demonstrated greater fire endurance period than equivalent thickness member made with concrete containing ordinary aggregate. The next part is the design procedure, where the design procedure starts with material selection followed by the aggregate selection. The coarse aggregate passing from the sieve of 20 mm and retained in 10 mm is preferred for the preparation of such concrete that absolutely don't need for fine aggregate. The water-cement ratio is ranged from 0.38 to 0.5. After that, the water content can be fixed. The binder content can be determined such as cement, lime, gypsum, slag, polymer. Next, we can determine the dosage of superplasticizer. The next step is to do the trial mixers test for density and strength properties. After that, we need to check with the standards so that the properties meet the standard requirement. And lastly, we can proceed with the final mix.
So, the first result for 4.1 inverted slump test. Based on the result as shown in table 2, the most significant finding is the inverted slump value for LWFC incorporating 5%, 10% and 50% of oil palm shell aggregates has reduced 7%, 13% and 18% respectively compared to LWFC CTR. The LWFC CTR had an inverted slump value of 788 mm while LWFC OPS 15 was only 643 mm. Next, for 4.2 density, according to the result, it can be observed that fresh and dry density in WFC CTR had the highest density and the lowest density is found in the LWFC OPS 15. The reason behind is the OPS has lower specific gravity as compared to sand, which result in reducing of overall density with the increment of partial replacement of OPS from 5 to 15% in the specimen. As such, the density will be lower compared to the control mix when no OPS aggregate were incorporated. And lastly, fire resistance test. As can be seen, the changes of temperature of LWFC OPS 5, LWFC OPS 10 and LWFC OPS 15 has reduced 19.1, 22.1 and 23.5% compared to LWFC CTR in 15 minutes mark. The reason behind the slower increase in temperature is due to higher porosity of concrete after incorporating OPS aggregate in LWFC, which caused the temperature having difficulties in transferring heat.
So, there are 4 major factors that can be discussed in this research. First is the flowability of lightweight foam concrete. The result indicated that mixing water was absorbed by the oil palm shell aggregates, resulting in decreased workability. As a result, additional increases in oil palm shell content are projected to result in even worse workability. Regardless of the variation, all inverted slump values exceeded 500 mm, the optimal slump value for self-compacting concrete. This might be explained by the high water-cement ratio used in this study. According to the earlier research, self-compacting concrete may be obtained by the use of high water-cement ratio of silica fume and ceramic dust powder in the concrete mixing process. Next is density. The reason for this is because oil palm shell has lower specific gravity than sand, which result in a decrease in total density when oil palm shell is partially replaced. As a result, the density will be lower than the control mix, which contains no oil palm shell aggregates. Moving on to compressive strength. Previous study shows that compressive strength is directly related to dry density of concrete. The denser concrete will undoubtedly withstand greater pressure. Due to its denser characteristics, lightweight foam concrete control could withstand greater compressive forces than lightweight foam concrete having 5, 10 and 15% oil palm shell content. Thus, compressive strength is projected to be inversely related to oil palm shell aggregate replacement. After 28 days, all specimens had reached 3.5 MPa, which is sufficient for concrete wall panels. Early compressive strength will be greater than later compressive strength. As a result, the compressive strength was expected to increase during the curing process. Lastly, the fire resistancy. For 5, 10 and 50% of the oil palm shell content, the temperature changes will decrease compared to the controlled one. The slower temperature rises in 5, 10 and 15% of oil palm shell content are owing to the greater porosity of concrete after adding oil palm shell aggregates to lightweight foam concrete, which causes heat transmission issues. Moreover, the oil palm shell aggregates exhibited superior thermal insulation capabilities compared to the usual fine aggregate, which is the fine sand in this instance. The impact is exacerbated by increasing oil palm shell, resulting in higher heat absorption.